All right, so we're in chapter 8 now. We're looking at graphs of trigonometric functions. And even though this chapter only has 3 sections, section 8.1 in particular has a lot of content that we need to cover. So let's go ahead and get to it. Back in chapter 7, we talked about definitions for the 6 trigonometric functions, and we defined them in terms of the unit circle. And again, I'm using the word function here. It's important to remember what a function is. We think of functions as some kind of a rule or formula or something like that that takes inputs and then produces outputs. So in the form, or in the case of a trigonometric function, a function like sine of x, for example, takes x as its input and then produces some other number as its output. But what do we think of that number x as? Well, in chapter 7, we were thinking of the input of this function as an angle, and we associated that angle with some angle made by the unit circle between the positive x-axis and some radius of that unit circle that we call the terminal side. So we think of these inputs as angles typically, and the output corresponds to a coordinate or the coordinates of a point on the unit circle in some specific way, and how we get that value depends on which trigonometric function we're talking about. So for example, the sine function, if the input is some angle, then if we think of that angle as being on the unit circle in standard position, then sine of that angle corresponds to the y coordinate of the point on the unit circle that determines. In this section, even though the unit circle is underlying all of the work that we do with our trigonometric functions, we're going to start moving away from the unit circle idea in a graphical context. And specifically what we're going to do is think about how you normally graph functions in algebra. When we graph functions in algebra, we graph them in the Cartesian plane on x, y coordinates. And we think of the x-axis as being the axis that we get our inputs from. We plug in x values into functions. And then the outputs we think of as y values. So those correspond to values on our y-axis. We want to do the same thing with our sine and cosine functions in section 8.1. And then we'll look at the same concept in 8.2 with all of the other 4 functions. So in order to do that, again, even though the angles, the inputs that we plug in for our sine function, which we're going to consider first, are normally thought of as angles, we're going to start thinking of them as just numbers that live on the x-axis to get a graph out of this thing. And so if you think about in algebra, anytime you graph a new function for the first time, you create a table like this one. You have a selection of x values or inputs that you plug into your function, and then each one of these gets plugged into your function, producing some output, which we see here. And then you use these pairs of values to create points or ordered pairs, and then you plot those points and try to put a curve through that graph. And here's what that would look like in the case of our sine function. If I plot the points that I get by using x values from 0 to pi, and notice the numbers here are all values that are 1, radian measure, and 2, show up on our list of common angles from the unit circle, pi over 6, pi over 4, pi over 3. I'm only using these values because these are values that I'm readily able to find the sine of, because we've memorized the unit circle. Okay, having plotted these points, you're seeing them on this graph here, and notice we're only going from 0 to pi in this table, but if I continued plugging numbers in from pi going all the way to 2 pi, we would see the graph do this thing where it goes below the x-axis and comes back at 2 pi. Okay, so this is what the graph of the sine function would look like based on plugging numbers in. However, it's important to remember that the domain, and remember in the language of functions, the domain of a function is the set of all possible inputs, the set of all numbers that you're allowed to plug into that function. The domain of the sine function and the cosine function, for that matter, is all real numbers. So the graph is actually bigger than just this. We're only looking at a piece of it. We're going to see in a moment what happens if we were to continue graphing beyond 2 pi. But before we do that, I want to look at how this graph relates to our unit circle. So here's a piece of that graph that we just drew, or that we just looked at. And here's a unit circle to the left of it. Remember, these x values down here, you're seeing a 0 at the origin, pi over 6, pi over 4, pi over 3, pi over 2. This is about where they would live on the x-axis. In the unit circle, these numbers correspond to angles. So you're seeing this red terminal side, this green terminal side, and this orange terminal side corresponding to the angles pi over 6, pi over 4, pi over 3. Those angles are now being thought of as x values on the x-axis. What is the sine of each of those angles? Well, the sine of any angle, like we said before, corresponds to the y coordinate of the point on the unit circle that angle takes us to. So if that pi over 6, for example, if pi over 6 is here, I can find the y coordinate of that point by kind of tracing it back to the y-axis and locating that value. But notice if instead of moving to the left, if I move to the right over to the second graph over here, that's where that y coordinate would live. So pi over 6, when plugged into my sine function, gives me 1/2, which is right here. And then as I kind of move through that first quadrant, sine of each of those values gets a little bit bigger. We're at 1/2, then root 2 over 2, and then root 3 over 2, and then finally up to 1 when we get to pi over 2 here. So this is sort of a visual connecting what we've done with the unit circle to the way that we're going to sketch graphs in Chapter 8. Okay. Here I'm doing the same thing, but with the cosine function. We really just look at sine and cosine in this first section. Again, table of values, and I'm using the same x values in the first two quadrants, 0 through pi. And we know from Chapter 7, these are the values we would get out of our cosine function by plugging these in. If you plot those points, you're going to see that you have positive values up until pi over 2. That's like the first quadrant of the unit circle. And then we know that cosine is negative in the second quadrant from pi over 2 to pi, so it dips below the x-axis. It goes down to here. And then if we made our table bigger and went to 2 pi, we would see this graph ultimately getting back up to 1, where we started from. Okay? So like I had said before, this is our graph of cosine. Here we had our graph of sine. In either of these two cases, we're only looking at a small piece of our graph. We're specifically looking at the portion of our graph on the interval from 0 to 2 pi. But again, the domain of both of these functions is all real numbers. There's more that we could have plugged in outside of this small interval. And if we were to do that, what would you expect to happen? Well, both sine and cosine, as we talked about in Chapter 7, are what we call periodic functions. Periodic functions with a period of 2 pi. And what that means is that every time we go a distance of 2 pi along our x-axis like this, the graph will start to repeat itself in further intervals of 2 pi. We call those intervals, or those lengths of 2 pi, the period of the function. So in this case, I could say that I graphed one period of the cosine function. Another term we use for that is cycle. So I've graphed one cycle of the cosine function. If we were to continue this and go in another distance of 2 pi, so stretching this out to say 4 pi, I should expect to see this entire shape of this graph repeated from 2 pi to 4 pi, and then again from 4 pi to 6 pi, and so on and so forth. And so what you get, instead of just this one little slice of the graph, is something that looks like either of these two graphs. Here's the graph of our sine function. Again, over here, we only graphed from 0 to 2 pi, but kind of zooming out a bit, you can see from 0 to 2 pi, that's this portion of the graph. And notice how it starts at the origin, goes up, hits a maximum value of 1, doesn't go any higher than 1 anywhere else on the graph, then shoots down to -1, and then by the time our x's get to 2 pi, our y's have worked their way back to 0. So we've kind of returned to where we started from, and then we're going to repeat that cycle over and over again in lengths or periods of 2 pi. So here's that one period of 2 pi that we're seeing right there. Cosine, similar. If we zoomed out from this graph up here, we start high at a maximum, work our way down low to a minimum, get back to high again at a maximum as we work our way from 0 to 2 pi. And we're seeing the same thing happening here. 0 to 2 pi, I start high, go low, go back to high again before I start over again. Another thing that we discussed in Chapter 7 was those even and odd identities. for the sine and cosine function. And I think I mentioned a little bit about what that implies about the graph of a function. Odd functions have what's called odd symmetry, or in other words, we also call that symmetry about the origin. And again, the idea is that if you just look at this half of the graph of our sine function, so everything to the right of the y-axis, if you were to take this, reflect it across the x-axis, notice it would bring this maximum value down to a minimum value down here, and then take that reflected graph and reflect it again, but across the y-axis, you would end up with the exact same thing that you see on the left-hand side of your y-axis. So it has that odd symmetry that we expect to see, but now we're actually seeing it in this graph. Cosine has even symmetry. That's symmetry about the y-axis. So again, if I took the right-hand side of this graph, everything to the right of the y-axis, and reflected it across to the left side, I would get this exact image right here. So both kinds of symmetry are now apparent since we can see these graphs. Okay, we haven't done any examples yet, and we're not going to do any examples for a little while because we actually have a lot to work through, starting with this topic of sinusoidal functions. So a sinusoidal function is basically a way of taking either a sine function or a cosine function and making it more complicated in a very specific way. They're functions of this form: y equals a sine of bx minus c, notice the parentheses, plus d, or what looks essentially the same but having a cosine here instead of a sine here. The a, b, c, and d here are all constants. We think of these as just different kinds of constants that we could plug in. It's important to note also that there is a minus on the inside here. That's important. If we see a plus there, we have to think of c as a negative number. And again, here's what I mean by that. Bx, if I were to write bx plus c, mathematically that's no different from this, bx minus negative c. Now the reason that matters is because if I'm seeing, and we'll encounter this as we kind of get to the examples towards the end of this section, if I see a plus in the parentheses here, I need to interpret it as a minus, and that means I have to think of whatever number I have here as a negative instead of what I would normally think of as a positive, because this number is going to be used for something later on, and if you don't give it the correct sign, it's not going to come out right. So what we're trying to do is determine what impact the a, b, c, and d in each of these sinusoidal functions has on the graph of sine or cosine, the graphs of the functions that we just looked at. Got that right now. Okay, what will those do to these graphs? The key thing here is to remember from algebra what function transformations are. This is something that's typically covered in intermediate algebra, and we don't have the time to do a full review of that because that's prerequisite material, but we will just briefly talk about what those transformations are. There's three different kinds of transformations that we have to consider here. You have what are called translations. Those are also called shifts, and those can occur as horizontal translations or vertical translations. So if you have a function f of x, and then if you add or subtract some constant from the input, so f of x minus h or f of x plus h, that creates what's called a horizontal translation. Here, if we think of h as a positive number, if this is a minus, then you're going to see a shift to the right. If it's a plus, you're going to see a shift to the left. Okay. Vertical translations also come from either adding or subtracting a constant, but that happens outside of the parentheses of our function, f of x plus k, f of x minus k. If we think of k as a positive number, then adding k will shift our function up by k units, and if we subtract a positive number, we're shifting down by k units in this case. Okay, so both of these are called translations, and that's how those translations work. Down here is another kind of transformation that can occur. It's called a reflection. For us, we really only need to consider one type of reflection, and it's reflections over or across the x-axis. Those occur if you have a negative number in front of your f of x, a negative value in front of your function. Okay, that takes your graph and flips it. If it's just a negative, then all it does is reflect it. If it's in -2 or something like that, then it's going to be a combination of a reflection and a stretch or a compression, which we'll talk about next. So here, you'll notice it only discusses vertical stretches or compressions, but you can also have horizontal stretches or compressions. And again, here the black graph, this is a parabola in this case, is what we call the parent function. It's the original graph. In our case, it's going to be not a parabola. It's going to be like sine of x or cosine of x. But if you multiply that function on the outside, so a times f of x, where a is a constant, then that's going to create a vertical stretch or compression. Think of this parabola, for example, as a rubber band. And if you take the ends of it, which technically there are no ends of it because it goes forever in both directions, but if we sort of imagine kind of pinching the parabola here and pulling up, it's going to stretch that parabola and make it narrower. So that's what we would think of as a vertical stretch. A different sort of related transformation is a compression, which is like if you imagine this parabola as being kind of squished down, and that would cause it to widen, creating this red parabola here. Okay, it gives conditions on whether you're looking at a stretch or a compression. We'll look at that in more depth when we talk about, actual sinusoidal functions. But when talking about function transformations, this vertical compression or stretch occurs by multiplying the outside of your function by a constant. One thing we also need to consider is what happens if you multiply the input x by some constant. Notice that's what's happening here. So in the parentheses, where I have this bx minus c in my sinusoidal function, the stuff in parentheses here corresponds to what's happening in the parentheses in any of these transformations. Notice that this x has a constant that's multiplying to it. That constant will result in a horizontal stretch or compression. The way in which that affects our sinusoidal functions specifically is what we're going to go over next. So this was just meant to be a very brief run through of the kind of transformations, and now we're going to get into the nitty-gritty of all this. Okay, so what we're going to do now is take a look at our sine and cosine functions and investigate each one of these individually. Starting with what we were just talking about, a horizontal stretch or compression. Notice here we have parts of 3 different graphs all sort of superimposed over each other. The blue graph is the one that we've already looked at, sine of x. We saw it on the first page, and remember it starts at 0, goes up to 1, works back to 0, down to -1, and then back to 0 again before it repeats that cycle. So there's one period of your sine function. What if I look at the function sine of 2x instead of sine of x? Well, that you can see corresponds to this red graph. And if you notice, one period of this red graph is just from 0 to pi. Notice it starts at 0, goes to a maximum of 1, 0, minimum of -1, back to 0 again. And now it's going to repeat itself. So in the length of x-axis that the blue function took to complete one full cycle, the red function is completing 2 cycles. It's oscillating faster, and that's corresponding to this 2 here. Okay, so essentially what that does is it doubled the rate at which we complete cycles in our red graph compared to our blue graph. Another way of interpreting the same thing, and this is the way that we need to interpret it for what we do, is that it shortened the period of the red graph by a factor of 1/2, which is the reciprocal of 2. Okay, now take a look at this green graph. This is sine of x over 2, or it might be a little bit easier if we look at it as sine of 1/2 x. It's the same thing. So b, the constant that's being multiplied to x here, is 1/2. And notice what that did is it stretched the graph out. In fact, from 0 to 2 pi, it's only completed half of its period. It's going to have to go another distance of 2 pi to get back to 0 again and complete that cycle. So in this case, the period has actually been stretched out by a factor of 2, which is again the reciprocal of this. Okay, so let's see if we can generalize this now. What we want to do is take a look at kind of a general graph for a function of the form f of x equals sine of bx, where b is just some constant, any constant. Okay, now based on what we saw up here, the larger b is, the smaller the period becomes. And again, that's the red graph, which had the largest value of b but the shortest period. On the flip side, the smaller b is, the larger the period becomes. So we want a formula to come up with exactly what that period should look like in terms of b now. So going back to our original parent function, g of x equals sine of x, in this case, we know that this function completes one full cycle over the interval from 0 to 2 pi, because that's the period of that function. But the x here comes from the input on our sine function. If we're looking at the function f of x equals sine of bx, the input doesn't look like x anymore. It looks like bx. And so that bx is what should be showing up in this interval here. What we need to do is solve this inequality for x to determine what the true period is for this function. Now, if b is a positive number, I can solve for x by dividing everything by b. This would still be 0. Notice we have x here now, and here I have 2 pi over b. I made the assumption that b was positive when I did that, and the only reason for that is because when we divide by negative numbers, inequalities flip over. That's something that we learn in algebra. So if b is a negative number, I can still divide everything by b, but the only thing that's going to change is that my inequality symbols are going to flip around. I can flip the entire thing the other direction and write that this way. Remember, b is a negative number, so 2 pi over b would also be negative, making it less than 0. It makes sense for this to be on the left side and 0 to be on the right side. In either of these two cases, whether b is positive or b is negative, the length of either of these intervals is 2 pi over the absolute value of b. And again, that absolute value is necessary because in one of these cases we considered what it would mean if b were a negative number, giving me a negative value overall, but you can't have negative lengths. Remember, the period represents a length. It needs to be a positive number. So 2 pi over the absolute value of b, that gives us the period of a function that looks like this. Okay, we'll summarize this result with all the others we're about to come up with a little bit later. Okay, you're gonna get a lot of information right now, and then we'll run through some examples in a later video. Next thing I want to consider is the idea of vertical stretches. How does that affect our graph? And for this, we need to introduce some terminology. So I've already been referring to some values as maximum and minimum values. But let's go back to these graphs to see those a little more clearly. Our sine function, when we're graphing it, never goes any higher than a y value of 1. And so I would say that the maximum of this function, of the sine function, is 1. Maximum referring to its largest possible y value. The minimum of the sine function is -1 because this never dips below -1. The same is true of the cosine function, maximum of 1, minimum of -1. Okay? So again, we call that maximum and minimum. Now the line that passes the horizontal line, which in this case looks like the x-axis, that is equidistant from the maximum and minimum values. So again, there's a lot of horizontal lines that I could draw through this graph, but only one of them is the same distance away from a maximum value as it is from a minimum value. Both of these have a distance of 1 from those extreme values. That line that passes right through the middle of the graph is what we call a midline. Okay? And then the height or distance from the midline to either the maximum value or the minimum value, because again, they will be the same distance, is what we call the amplitude. Okay, so in this case, the x-axis is the midline, and the distance from the midline to either a maximum or a minimum value is what we call amplitude, the amplitude of this graph. Okay, so I define those terms here, and I want to see how different values of remember those sinusoidal functions have an a, b, c, and a d in them. Which of those numbers affect amplitude? Which of them affect midline? So let's start by looking at amplitude. If I have a function of the form f of x equals a times sine of x, or a times cosine of x, From what we know about function transformations, multiplying a function on the outside by a constant creates a vertical stretch. And naturally, you can see from this picture here that those vertical stretches are going to change the amplitude of our graph. They're not going to change the midline, they're going to change the amplitude. There's 4 sine functions that are graphed here, and each one of these only differs by the constant that is being multiplied by. So you can see red, blue, green, and orange. I'm multiplying by 1, 2, 3, and 4 respectively. And correlating those to the graphs shown here, you can see that every time I multiply by a different number, the amplitude is stretched. It's stretched to a larger value the larger that this number is. In fact, like I said, the midline hasn't changed. The midline in this case is still the x-axis. Look at the yellow graph. I multiply by a 4, and now the distance from the midline to my maximum value is 4. My amplitude is 4. Same thing for the green graph. I multiplied by a 3. The amplitude visually can be verified to be 3. So it looks like that constant gives us our amplitude. Or in other words, if I have a graph of the form f of x equals a sine of x, or g of x equals a cosine of x, it looks like the amplitude is exactly equal to that a. However, none of these graphs consider what happens if that number is a negative number. Remember, amplitude is a measure of distance, so you can't have a negative amplitude. Take a look at this graph down here. This graph is similar to this yellow one, except instead of multiplying by 4, we're multiplying by -4 right here. And look what happens. Normally, a sine function would start at 0, go to a maximum, then go back down to 0, then go to a minimum, and then back to 0 again. But this one did the reverse. Instead of going to a maximum, it went to a minimum. In fact, what we're seeing here is a reflection about the x-axis of this yellow graph here. So that's what the negative does. It flips the graph upside down. But then if you look at the amplitude of this graph, so from the midline to a maximum or from the midline to a minimum, that distance is 4, which is the absolute value of that constant. So this gives us a good generalization. If we have a function of the form f of x equals a sine of x, or g of x equals a cosine of x, the amplitude of that graph will be the absolute value of this constant a. Again, we're going to summarize all of these important results later. This video is kind of getting long, so I'm going to stop this one here and pick up where I left off in the next one.